All right, so similar reminders as last time, but the slight shift is that the concept check 5 is now due this upcoming Sunday, so I shifted it from the previous Sunday, but otherwise pretty much the same. So you all are still looking for resolving one group issue, but otherwise pretty much all the groups are set. So the algorithm choice assignment is due Saturday nominally. So that gives me some time to look through those and provide some feedback. See there's a document of candidates on Canvas. So if you go to this assignment, it links to it. If you also just go to the final project module inside Canvas, then there is a link at the top for this document, which has a list of candidate algorithms you can use on your final project. If there's one that you think is appropriate for this class or a significant extension of one that we have already discussed that is not on that list, then you can propose your own choice and then have me take a look, and then I can say whether that makes sense or not. Then after that, the next deliverable will be in April, mid-April, the final project proposal. So that will be a short proposal, something like 2 pages or something like that. There's some guidance on that, and it basically, even I think less than 2 pages, and it basically tells me beyond just what algorithm you're going to be doing, but roughly speaking, how you're going to exhibit or demonstrate properties of that algorithm. So what is you're like, I'm going to decide I'm going to apply this algorithm to this particular application case, and I'm going to take these metrics. I expect to get results like this. I mean, you don't have to actually have it done or anything like that. Just give me an idea of what you're doing, what you're planning on doing. Otherwise, the muddiest points, like so, the concepts check for this previous Unit 5, and then the mini project for Unit 5 also is coming up. So, any questions about this stuff? Okay, then otherwise, I wanted to, especially motivated by this concept check, I wanted to make sure we had sort of concrete definitions and kind of clean formulations for the end of this Unit 5. So to start this lecture, I've got a bunch of sort of canned stuff that we can kind of see down here that rather than me writing out, we'll eventually get back to that. So I'm going to go through this a little bit, get back to me writing things down and slowing the pace down. So we're going to go through the stuff that I've got covered up here a little more quickly than usual, but it will be in the notes and be there as a reference. And so some of this is review, some of this is trying to make our previous discussions a little more rigorous, and then also provide us a foundation to finishing up simulated annealing and then move into swarm intelligence. Okay, so from last time we talked about a macrostate. Basically, if we wanted to define it, is a distribution of microstates. And so there's a bunch of very small configurations. So configurations with lots and lots and lots of degrees of freedom. We group them into these kind of equivalence classes. We group them into these things that we call macrostates, which represent distributions there. And so let me just change this to tape eraser. So thermodynamics and statistical mechanics provide tools for thinking about macrostates and microstates. And so thermodynamics provides tools for thinking about macroscopic properties like entropy, but also like temperature, pressure, things like this, things that may actually be properties of macrostates. So I can say that there's a certain pressure in this room. That is a macroscopic variable of the distribution of particles in this room. So there is a relationship between those observable macroscopic properties in thermodynamics. So how does the temperature change over time? How does the pressure change over time? And the underlying configurations of the particles in the room, which fall under statistical mechanics. And so that's where we have ideas like entropy, which sort of say, of all of the different microscopic configurations that this room could be in, which ones would we expect at equilibrium? So that underlying sort of math of the microstate tells us which macrostate we need to use when we then do macroscopic calculations in thermo. So those two things up there, given the description that I just gave, it may not, hopefully it's not a surprise that they're built on top of probability and information theory. information theory, which itself is sort of built on top of probability. And so really, these application areas in physics nowadays we might view as applied probability and applied information theory. Although at the time, sort of the thermo kind of came first and the statistical mechanics kind of came first, and then they kind of co-evolved with each other and have had a lot of cross-pollination since then. All right, so that's kind of setting up the foundation of what we've been talking about in terms of setting us up for simulated annealers. And so if we want to along those lines, kind of our fundamentals of information theory and thermo and stat mech, we need to talk about random variables. And so we've now gone from talking about particles in the room and now just talking about general distributions of things, which should be interesting to us as computer scientists, as industrial engineers, as data scientists, because we describe the world probabilistically. We describe the world, the things we don't know about the world, as coming from probabilistic distributions. So this, framing things in terms of probability and information theory gives us a gateway where we can take insights from the physical world and import them into the digital world or the data world. So, I'll talk about random variables, and that random variable could be discrete, so it has a probability mass function. It could be continuous, so it has a probability density function. But for both of those, we can define what's sort of at the heart of entropy, which we've been talking about, is this idea of surprisal or self-information. So for any outcome, we can look at its probability, and if it is a low probability, we would say it is surprising. And if it is a high probability, we'd say it's not surprising. So the surprisal value of an outcome is the negative logarithm of its probability. So it's just mapping probability to log effectively, or it's mapping, I would say, 1 over probability through a logarithm. So if it's a small probability, then 1 over that probability is going to be very large. So log of a large number is going to be a large number. So small probabilities are very surprising. If it's a large probability, 1 over a large probability is going to be a small number. A log of a small number is a small number. So that's where we get surprisal. And then this generalizes to continuous distributions and so-called differential surprisal or information content at a point. That's kind of going beyond the scope of what I care to go into here, but just putting in there for completeness. Now I've used the logarithm here. And again, all of this is, of course, going to be in the notes, but and we can choose what log to use there. And different practitioners use different logarithms for these things. So if you use log 2, log base 2, then the units of these surprisals are in bits. So that's kind of the most common. But in physics, it sometimes is actually convenient to use the natural log, in which case the units are nats instead of bits. There are other application spaces where it's just more common to use the common log or base 10, in which case these information measures are in Hartleys or bands. It's a lot less common. In a lot of the context you'll see, it's just bits. But I just want to emphasize, it doesn't really matter what base you use here. It might affect the way you interpret these things, but it's all the same. It's just scaling it by a constant. So that's why I'll generally refer to it in terms of bits. All right, so that's that's the definition of surprisal. Some sort of examples of that. Again, if it occurs with 100% probability, then there's no extra information needed to say what's going to happen. So that's kind of what we mean by there's no surprise. So if you know it's going to happen, if you know when you walk into a room, there's no chance the lights will be off, then telling someone that the lights are on carries no value. There's no surprise. So you just may as well not say it. So that's what we mean by if it happens with 100% probability minus log of 1. Well, log of 1 is 0, so the minus doesn't matter. That gives you 0 surprisal. Likewise, if it happens with 50% probability, there is potentially some surprise. If it's I'm walking into the room, I don't know if the lights are going to be on or off, there's equal chance they could be either one, then it's going to be surprising when you open the room. How surprising? It'll be 1 bit surprising. And what that means is there'll be that's how much uncertainty will be resolved by doing the experiment, by going into the room. So that is how many degrees of freedom are left over when there is a 50% probability. So if your sort of macro state, if your room is the set of all rooms for which lights are either on or off, then that's the surprisal value, 1 bit. So you can play this game further and you can say, well, okay, so if an outcome occurs with 25% probability, we should expect this as surprisal is higher. And so how do we then, make sense of this formula? Well, if it happens with 25% probability, then if I want to sort of communicate what actually happened, it's most efficient for me to use 2 bits to describe this outcome and fewer bits for more likely outcomes. So as an example, if there's 2 outcomes, one that happens with 25% probability, the other that happens with 75% probability, then somehow that should be less surprising on average as the system where both outcomes are 50%. Or in other words, if one outcome is very, very likely and the other outcome is not so likely, then the very, very likely outcome should somehow be less surprising, closer to 100%. And the less likely outcome should be more surprising. So, and the total distribution, the total entropy in the distribution should somehow be a blend of it. So that's why when we say if an outcome occurs with 25% probability, well, 1 over 0.25 gives us 4. Log of 4, if you use log base 2, gives me 2 bits. So we say there's 2 bits of surprisal in something that's 25% likely. And a way you can kind of make sense of that is if you were trying to code this in a binary code, you could say if the common case happens, then I'll just give you a 0, a single 0, 1 bit. But if the uncommon case happens, then I'll give you 2 bits. So I can't give you a 0 because 0 will then tell you that it's the common. So I have to give you a 1, and then just to confirm that it's real, that actually happened, then I'll give you another 1 as sort of an error correction. So you can kind of think of that as like the common cases. You can just say, yep, everything's normal, everything's normal, everything's normal. But then in the uncommon case, then it's surprising. So you give 2 bits to sort of make it very clear that actually it's a rare event that has occurred. It's not just sort of a mistake in communication. So it's sort of this, can you repeat that type of idea, is that things that are less likely are more surprising. And so it is more likely that someone is going to say, wait, did you just say that pigs were flying? And then if someone said that, they'd say, well, you could have just said that. Could you repeat what you just said? And then if they say again that pigs were flying, then well, it's probably not a coincidence that they just said some crazy thing twice in a row. I probably didn't mishear them. Actually, I have to believe them, pigs are flying. Of course, pigs are flying is so rare that you'd probably ask for another repetition and another repetition, just to make absolutely sure that you understood what they meant. So the surprisal value, how many bits, is sort of like how many questions are you going to need to be satisfied that that rare outcome actually occurred if someone communicated that to you. That's what we mean by surprisal. And then from that, we can then define entropy, which is going to be average surprisal. So, and then I'll pause for questions here. So the idea here is that, if Shannon entropy, which I didn't define this term before, I didn't use this term before, but when we define entropy in this form, where typically we're going to use log base 2, but in this form here, if I'll use H, notice I don't have any K terms. I don't have any Boltzmann's constants there. So when you strip out the Boltzmann's constant, it's just referred to as H, or Shannon entropy, as opposed to S, which is the kind of physical entropy, which we'll get to here. And so Shannon entropy, otherwise known as Shannon information, they're synonyms for each other. That's the uncertainty about the microstate, given you know what the distribution is, given that you know what the macrostate is. And it's basically just the average surprisal value. So that's what this formula is here. It's the expected value of the surprisal formula over the distribution of your random variable. And if you want to do it with continuous, then there's the continuous form, but it's the same thing. It's this expectation of surprisal. And so it's the average surprise across all outcomes. And so that is also going to be in units of bits, nats, Hartleys, or bands. Typically, you'll hear bits. In the physics community, you might hear nats, but it's just a scalar. It's all the same. So bits is sort of it's kind of the easiest to interpret. But then when you do get into those physics, then if all so leading up to then getting back to our number of microstates count thing, if you set all of the probabilities equal to the same, so this is like, for example, if I set pi equal to 1 over n, where you have n microstates, if all of these microstates were equally likely, then everything above breaks down into just, like you get a constant there, 1 over n. You get just the n inside there. All of the 1 over n's end up averaging out. So then all you're left with is a single log n, log number of microstates. So that's if all microstates are equally likely, not only is the simplest form, but that's also the maximum information you can get. So this is sort of the idea that if you just count the number of microstates, then you know that at max, I might have 40 bits of information, 40 bits of possible entropy. But then if somebody says, oh, but one microstate is much more likely than another microstate, then you're going to get less information, or you'll need less information to describe the system. There'll be less entropy in the system. So this degenerate form here serves as kind of an upper bound on the information. And then when we finally then extend that to sort of the roots of entropy, then we get this kind of Gibbs entropy, which is denoted as S. If you take a thermo class, this is the S that of the sort of famous delta S is greater than 0 from the second law of thermo. And so this is just scales Shannon information by the Boltzmann constant, and it typically uses natural log. So it's Shannon information in nats scaled by Boltzmann here. So whereas this I interpret as the amount of uncertainty about a microstate, given that I know the macrostate, given I know the distribution, then the way the physicists would interpret this is sort of the amount of disorder per unit temperature. So they're sort of saying that if you heat the system up, then the system will get maybe more flatter. They'll get more microstates excited, and this is sort of saying that if you kind of normalize out the temperature effect, then per unit temperature, how much disorder is left over, where they measure disorder per unit temp as joules per Kelvin. But it's just a scaling factor. So there are some reasons why it's convenient to have this unit on these entropy for downstream calculations that are out of the scope of this class. But for all intents and purposes, Gibbs entropy is just it's a scaled version of Shannon information. So when anyone says entropy, generally you can just think of Shannon entropy, but most of the properties you've heard about in entropy in physics that apply to this one also apply to this one. So they're effectively synonymous. They're off by this scalar, this Boltzmann constant here. All right, so that is a review of our kind of entropy, and I just wanted to make sure I introduced some of these terms like Shannon information, and make it kind of clear how everything relates to each other. I'll also mention up here, this is kind of this sort of explanation for why log. The nice thing about using a logarithm to define entropy or to define surprise is that if you have two independent events, that we know that their probabilities are just the products of each other. So the probability of event A and B. So what's the probability that I wear a blue shirt and you wear a green shirt? Well, those two decisions are decoupled from each other, and so they're independent. And so the number of shirts that I have to wear and the number of shirts that you have to wear, we're going to sort of set up the surprisal value for us individually. And then if we said, well, okay, well, what's the probability that I wear a blue shirt and you wear a red shirt? Well, now that combined event of the two of us together, that is just going to have the combined surprisal of my surprisal plus your surprisal. So that's, and that just comes again, that's one of the nice things about having a logarithm is that when you have independent systems, if you create a composite system, then you can just combine their entropies. You can combine their surprisal at the level of outcomes, and you can combine their entropies at the level of the system. All right, so any questions about that? It's just kind of wanted to make sure we get all this down rigorously. Nice little reference sheet. Okay, so moving back toward our simulated annealing. We started talking about this last time. At a given temperature T, what's the probability of a given microstate energy EI? So we know that every microstate you can evaluate and ask how much energy is in it. So if I hold up a baseball right here, I know how high it is. And so I can calculate if I were to drop the baseball, what speed it would hit when it hit the ground, because I know how much gravitational energy is in the baseball when I hold it at this height, this height, this height. And so I can calculate, can convert that into kinetic energy, and I can see then that's how much energy was being stored in that ball. So theoretically speaking, if you knew every description of every molecule in this chair, then you could figure out, which molecules had a coulombic, had a kind of an electric attraction to each other that was being stressed, tensed out, that they kind of wanted to snap back together. So that would be like higher energy, which one was kind of lower. And so you could figure out for every microstate, as complicated as it would be, has an energy that you could kind of calculate. So given that every microstate has an energy, then we can say for a given temperature, what's the distribution of energies, which effectively sets up the distribution of microstates. Because if certain energies are just too high to be available at that temperature, then those microstates are going to be out of bounds as well. So it would be nice if we had this mapping right up here. What is the probability of a particular energy, which is effectively the probability of that microstate or microstates at that energy. So, that we can solve this with maxint. So we have constraints here. So this is how you use maxint. It's how you use it in natural language processing. You download the maxint library from Python. It has, you can put in a list of constraints, and then it will then spit out a maximum entropy distribution or draws from maximum entropy distribution subject to those constraints. Here are our constraints. We were told that it was a probability distribution. We are trying to solve for these PIs. What do we know about the PIs? They're all greater than or equal to 0. What else do we know about them? They're probability distribution, so they all add up to 1. So that's one set of constraints that we know. What's the other thing that we know? Well, we know that we are interested in a system which is, and now I used K, this is the Boltzmann constant, I just got tired of writing all the little B's. We know that the average energy of the system is related to the temperature. So we know that the system's at equilibrium and the temperature is proportional to the average energy in the system. Well, on the left here, this is the formula for average energy. So these are the energies across my outcomes. These are the probabilities for each of our outcomes. So this is the average energy. I know that temperature is related to average energy through the Boltzmann constant. Boltzmann constant is just a constant proportionality. And so this is just saying here that for this temperature, there is a certain average energy, and that must be equal to the average energy across that. So of all the probability distributions out there, then we only care about the probability distributions that have this going on. So we need to say, all right, so there are probably lots of probability distributions probability distributions that have this going for them. We could dream up several of them and write them on the board. We don't care about all of them, though. We say that we only care about the ones that are be at equilibrium. We'd expect to find, as time goes to infinity, after everything's shaken out, where there's no other constraints or information sources acting on the system. So nobody else, people might have started out by moving things around, microstates around, and creating these sort of rare states, rare microstates, making them more common. But that's let go because we're saying that force is not there. So given there are no other forces acting on the system aside from the ones tied up in these constraints, what is the maximum entropy? Because we would expect that's where the system's going to go over time. And so you can, if you've ever taken a course in optimization, on constrained optimization, it's fine if you haven't. I'm not going to ask you to do this, but if you ever have done this, because this discrete problem can be solved with Lagrange multipliers. So if you've ever solved a constrained optimization problem, you can basically say, I'm going to take an entropy formula off this page. I'm going to take this entropy formula here, and I'm going to choose to maximize that entropy formula. And I'm going to adjoin to the system via its Lagrangian these three constraints. And that's relatively easy to do. I don't know why we don't teach this in high school, because it's the right way to do optimization and it's not that hard. And I think it's because it has these ugly names like Lagrangian. It's kind of scary, but if we just would rename it to make it prettier, then we would teach optimization right at the lower levels. But so if you've never done a constrained optimization problem, I highly recommend looking into KKT, the Karun-Karush-Tucker conditions, and Lagrange multiplier theory. It's a really nice tool to have in your toolbox. But so we're not going to go through just saying, trust me, you can turn this maximize this subject to this, and it turns that complex sounding problem into a relatively easy problem to solve. And from there, you get not that, you get this out. So you can solve for this directly on the back in the space of an envelope. You could solve this. It's pretty easy to solve. To go from there, maximize that entropy formula, and you get this. And this out here is what I've called the Boltzmann distribution. It's also called the Boltzmann-Gibbs distribution. So I think in the concept check, sometimes I refer to it to the Boltzmann-Gibbs distribution just to be complete. But it's the same thing. Boltzmann or Boltzmann-Gibbs distribution, it's the same thing. And then it looks uglier than it is. The numerator is referred to as the Boltzmann factor, and the denominator is a partition function, which for the purpose of this class is just a normalization constant. It just makes sure that this here holds. So if you solve this using Lagrange multipliers, then effectively this will just pop out easy. And then once you get all these PIs that you know must take this form, then in order to meet this constraint, you'll end up adding them all up together and dividing them. And that's where you get this normalization term down there. It's just all of the numerators added up, and then you divide by that. Now, it turns out that physicists get really excited about this partition function because it's a generator of all sorts of other properties. So you want to know the heat capacity of this system. Well, it turns out the heat capacity of the system is the variance in its energy states. And so there's ways to then use this to generate those moments. There's all sorts of properties you can ask about a system. And if someone gives you the partition function, then like a generator would for a probability distribution, like a characteristic functions and so on, then you can easily derive like 15 different things just by knowing the partition function. But for our purposes, when we look at this formula, which we're going to see, well, we're really going to focus on the numerator in the simulated annealing, then this is just a normalizer. But it has a fancy name because it can be used for other things too. So it's called the partition function, Z or sometimes Q. And so that's our Boltzmann distribution. Any questions about how we got up to this so far? This is just an application of maximum entropy. So I'll just mention that here. This is just apply max ent to H from previous page plus those constraints. So you get this cool thing which describes this distribution of microstates or distribution of energies. And what are its cool properties? Well, what it's saying here, because of this negative right here and right here, what this negative, so remember, K is a constant, T is given. So T is a parameter, but we view it as a constant. So this down here is just a constant. So EI, that's the thing that we're talking about. What are the distribution of the EIs, the energies? And what this is telling us is that because of this negative right here, then low energies are going to have higher probabilities. So low energies are more likely, but high energies don't go to zero. I mean, they go to zero. They aren't at zero. So higher energies are possible, but they are just far less likely than lower energies. So this is why this can sometimes be called the soft min function. So if you're, in machine learning, we have the soft max, which is exactly this, but you just get rid of the negatives. And if you get rid of the negatives, then it flips this so by switching of sign, it becomes a soft max, where in that case, higher energies are more likely. So if you've never thought about the soft max, or then you basically at the end of a neural network, for example, let's say you're saying, I've got 10 different objects that I could be seeing in my computer vision algorithm, and my neural network is trained to classify them. And so I might have a layer of outputs which have 10 different indexes of how confident the neural network is that it's seen each one of those 10 categories. So here's something I'm coming in, it's a bounding box or whatever. What type of object is it? And it could be a dog, it could be a cat or whatever. And so there's a dog output, and that has, and it's going to have these numbers that are not normalized to each other or anything else. They're just these indices that represent kind of accumulated confidence through the neural network that it has seen a dog, a cat, a boy, a girl, etc. 10 of those. And then so it then needs to provide you with a probability distribution to say, how likely is it that this bounding box that I just saw in this image is a dog, a cat, whatever? And so what it needs to do is take all these indices that aren't related to each other, and it basically turns them into these energies, E, and it gets rid of this so that's a positive. That's what softmax does. And then it turns them into a probability. So it'd say, based on this grouping of confidences that it's coming out of here for all my different classes, all my different categories, what's the probability that this bounding box is a dog versus a cat versus a whatever? And then you get a probability distribution that sums to one that you can view as kind of a Bayesian posterior on what it's estimated as, it started out maybe with a uniform of, it could be any of these things that you provided, and now after it's looked at its evidence, then it gets a probability distribution where it's most likely a dog, but it could be a cat. It's probably not a book, those sorts of things. And so that all comes from using softmax to turn those sort of unrelated numbers into a probability distribution. So the soft min was the original, and it was the Boltzmann distribution, and it got generalized into the soft max, and that's what you see in machine learning and so on. So likewise with the soft max, if you have this parameter which changes how willing you are to sort of tolerate alternatives, like how much you want it to just be the one that is the max evidence or not. Likewise, this temperature here, at low temperatures, this probability distribution will collapse around just the very lowest energies. At low temperatures, at higher energies, this thing is going to very quickly go to zero. But if you make the temperature higher, then at higher energies, you start getting appreciable probability. If you make the temperature really high, it almost flattens things out across, all possible outcomes. So things get flatter and flatter and flatter with increasing T. And it's the same thing with softmax. You can adjust a parameter on softmax, and then it can make it can make it so that it becomes more of just a max. Like, I'm just going to take, of all my 10 possibilities, I'm just going to take the one that has the highest confidence, and I don't care about the other ones. And to make it a max, then you effectively want to make your temperature as low as possible. But then if you want to say, well, it might be these other things, and so I want to create a probability distribution that spreads things out a little bit, but still has a high mode at that high confidence level, well, then you can have higher temperature. It's the same thing that's going on with the Boltzmann. So questions about that? So this is what we're going to use to set up our little random walker inside our simulated annealer. I'll let you guys mull over that while I get out my notes. Okay. All right. So that brings us to the simulated annealer. So this is our goal, is we have a optimization objective that looks like this one. We are going to make that analogous to our energy function. So this is the mapping from microstate to energy. Like I said before, you pick up a tennis ball or a baseball or whatever, and there is a way to say for every height how much potential energy is in that ball. Well, we have a way to say for every configuration of our design system, how good is it? Or at least how does it, if you were to give me three, could I rank all three? Just like if I were to have three heights here, like let's say, well, this baseball's got higher energy than this baseball, higher energy than this baseball. Well, I could say, well, I don't know what the best design is, but if you give me these three designs, this is more costly than this design, and it's more costly than this design. So if I only care about the cheapest design, then it's got to be this one that's over here, this cheapest one. So there's some way to go from your design space to your optimization objective. The same way there's some way to go from a microstate to an energy. So we're just going to call the design objective, and we're going to treat this as a minimization problem. So any max problem, you can just put a negative in front, it becomes a min problem. And our optimization objective plays the role of the energy in our Boltzmann distribution, our Boltzmann-Gibbs distribution. So we've plotted our energy function. I put it in quotes here. It's just our optimization objective. And we would like to find the lowest energy configuration. We would like to optimize this design to minimize cost, for example, or to minimize something else, minimize energy used in production, whatever, minimize sound production while operating, whatever it is. So you'd like to find this right here. So you are going to start at some random configuration, and then you're going to initiate a local search where it is going to take little steps to the left and right, the same way a chair that's in a particular microstate with a little thermal agitation is going to go to nearby microstates, and then other nearby microstates, and then other nearby microstates, but it's going to kind of search nearby. And so our initial guess starts moving around, and we want to bias that search so that movements that go down the energy function are more likely than movement that goes up the energy function. So that hopefully over time, then it has a chance of eventually finding this minimum here. But the problem is you run into these hills along the way. So sometimes we need to, if it manages to find its way down here, it still needs the ability to go up the hill so that it can climb this hill to find this one down here. And so that's why we're going to try to play with temperature so that sometimes it'll have the ability to hop these hills, and other times it'll get stuck in them. So, but before we get there, so effectively what we're trying to do is trying to simulate the process that happens in physics where microstates settle down into their lowest energy configurations or near their lowest energy configurations. So we want to build a sampler that samples from the Boltzmann distribution, the Boltzmann-Gibbs distribution. So we want to build a sampler which simulates physics in our bizarro world where energy is our optimization objective. So we want to simulate a physical system whose energy is our whose minimal energy configuration is our preferred design in design space. That's what's going on in simulated annealing. So we have to figure out how to do that simulation. So how do we build this Boltzmann sampler? And once we have that Boltzmann sampler, then we can play with this temperature to actually build our optimization meta heuristic. All right, so that's the goal here. So this is what we need to do, is to build this sampler. How many people have heard of Markov Chain Monte Carlo, MCMC? This was the first MCMC, came from this. Not from simulated annealing. Simulated annealing then used it, but the first MCMC came from the physicists' desire to do this to make some of their job easier. And then once they had this in the so-called Metropolis algorithm, which we'll talk about, then that was generalized into the Metropolis that was generalized so that Metropolis Hastings algorithm, so you could use it for other distributions other than the Boltzmann, and then a bunch of other MCMC methods were built after that were faster or use less memory or could work in parallel and so on. But so this is effectively also going to be an introduction to MCMC or Markov Chain Monte Carlo as well. So to sort of see that, I hope you can see that this in the middle here, this is basically that is a Markov chain Monte Carlo sampler. So it's like, this, it starts at a particular point in the space, and then from there it moves to another point in the space. From there it moves to another point in the space, and so on and so forth. So it's a Markov chain. It's a Markov process where it's hopping from state to state to state, where its previous state is the only thing that predicts its next state is its previous state. So it has that Markov property. But hopefully its trajectory traces out something useful to you, which in our case will be traces out our energy function. Okay, so how do we do that? All right, so decide where I want to skip ahead to another point here. All right, so the punchline that we'll get to is how to decide whether to move from state I to state J. And we mentioned this at the end of last time too. And basically what we are going to use is a likelihood ratio at a given temperature. And so we have, this is a proposed state. And the question is, do we accept or reject it? And we're going to do that based off of a likelihood ratio of the Boltzmann constants. And so because the normalization, we're basically comparing the probability of one state to the other state under the Boltzmann distribution. And because the normalizations are the same, they drop out. So you're just comparing the Boltzmann constants and the numerators to each other. So this likelihood ratio is going to be the probability. So it's pi over pj, which is just going to end up being e to the minus delta ij over kt, where delta ij is equal to the difference between, I said ij, I'm sorry, I meant to say ji, just to be consistent with my notes, is just the difference of ej minus ei. And so if this is greater than or equal to 1.0, we accept state J, move there. Otherwise, except with pi divided by pj probability. And then that will effectively, this is a way then that we will sample from the Boltzmann. And this is going to be found in the Metropolis algorithm, which we're going to talk about now. And then simulated annealing combines the Metropolis algorithm with an annealing schedule, and then you have an optimization metaheuristic. So you go from something which just simulates a physical system to something which simulates a whole physical process that is used to create interesting physical quantities, but then now it'll also create interesting virtual quantities. All right, any questions about this idea? We're just using and we're going to sort of rederive this or kind of come to where it came from here again. But this idea, we use a likelihood ratio to set up an acceptance rejectance rule here, where we're saying, if the effectively, if the next state is, and I might have, yeah, and let me, I actually don't like the way, yeah, okay. So if you're wondering, it doesn't make, this should be a J in the top, and this should be an I in the bottom. This is the reason why I originally did the IJs backwards. So hopefully this makes more sense. This should be a J in the top and an I in the bottom. Likewise down here. Sorry about that. It's annoying to carry the notes, but I obviously need them. You'd think this would all be memorized by now. But this should make a lot more sense. So the idea here is if the jth state is more probable than the ith state, then definitely go there. Otherwise, if the jth state is less probable than the ith state, then go there with some probability. And this, if I want to translate that into energy, then what this is basically saying is this happens where J is lower energy. And then down here, this happens when J is higher energy. So we're saying that if you have proposed a microstate that is better, lower energy, better in design than the current microstate, go there. That one's better. Just take it. If the proposed change is worse, hotter, not hotter, worse, more energetic, it requires more energy to get there, then maybe take it depending on how similar it is. And so the threshold of how far you're willing to jump is going to depend on the temperature of your system. So that's what, if you have a high temperature, then you're going to get a lot of acceptance, even though you're going uphill. If you have a low temperature, then it's very unlikely that you're going to move uphill. You pretty much only move downhill. So I could also call this, downhill and uphill. Questions about that? Okay, so we'd like to know where this comes from. And so this Metropolis here, like to sort of, where does this name come from? Is it the name of is this a city? What's going on here? And so the history of this comes from Nicholas Metropolis. In a paper, so et al., from 1953. So it was a physical chemist. Remember, 1953 was the Wild West when it comes to these methods. They still used in here the middle square method. for random number generation. Middle square for random numbers for PRNGs. So if you're not familiar with that, there's the modern way we draw random numbers, which makes a lot of sense. It's kind of a chaotic sequence that has a lot of randomness or whatever. Back then, they didn't know how to do that. So they used these methods where you took a bunch of numbers and then you grabbed the middle digits and you squared them, and that generated other numbers, and you grabbed their middle digits and squared them. And if you didn't set them up just right, you got these awful sequences that would degenerate down to zero or where they'd start repeating. So it's kind of crazy that these stochastic methods, were coming up in this area when they didn't know even how to draw random numbers in a really good way. But it really shows how powerful they started to realize having the ability to draw random numbers was. Now we take it for granted. We have all of these methods based on randomness that just, if you think about it, like, oh, that's pretty interesting that randomness gives us so much power. But back then they were just figuring that out. And this is around the time of the first atomic bombs. Some of those things were developed with some of these methods. The whole Monte Carlo method was developed with Oppenheimer, and that was a code name for these first stochastic methods that, in order for them to talk about them without worrying about this stuff leaking out, then they just referred to them as Monte Carlo methods. So they didn't, say what they were doing. But Monte Carlo, reference to a casino. So this is like it was top secret stuff around this time, just coming out. Just been declassified. 50s, and people starting to figure out other things to do with it. And Metropolis was one of them who was interested in just general physical properties. And so Metropolis was using computational numerical methods to try to understand what we call equations of state. So if you've heard about uh, like the ideal gas law, whatever PV equals nRT, that's an equation of state. But if you think about it, like, how do you figure out that pressure times volume is equal to N times R times temperature? That, like, where do you where does that come from? And you can actually look for those relationships computationally. You can simulate a bunch of microstates and then solve for their macroscopic variables, their pressure, their volume, et cetera, and look for how they relate to each other and come up with equations of state like the ideal gas law. That's the type of stuff that Metropolis was looking into trying to make easier to do. Um, and so this was, an introduction of Monte Carlo methods to physical chemistry. And what do we mean by Monte Carlo methods? So, and this is probably all review for masters and PhD students, but I mean, a Monte Carlo method. So a Monte Carlo method for estimating pi, as in 3.14, 159, 26, 53, et cetera, that, the kind of a well-known one is, well, I can draw two uniformly distributed random numbers, let's say between -1 and 1. And then I can just count how many are in the unit. I guess in this case, how many are in the inscribed circle. So an idea there, like if I just draw that square, so I'll say I've got a square that looks like this. Just pretend it's squarish. So I'll draw my axes through here. I'll say this is 1, this is -1, this is 1, this is -1. And then if I've got a circle inscribed on the inside here of radius 1, let's see if I can make that fit a little bit better. I'll just make it a squiggly ovoid and not worry about making it pretty. All right, so if you draw these random points, they could land anywhere. They could land here, here, here. So each point is a uniformly distributed random number between -1 and 1, and it could be between 0 and 1. I'm just trying to make it easier. So each one of these is a random point that lands somewhere here. And then you can say how many are in versus total. So then you can calculate the number in circle divided by total draws. Well, the probability that you're throwing darts at a dartboard, and if you neglect gravity, then you can hit them if you're just randomly throwing them blindfolded at a dartboard, where maybe this is the whole wall and the dartboard is a circle inscribed in the wall. So you're just randomly winging these things, not trying to hit any particular point. Then you just, you take your blindfold off and you ask how many things actually landed in the circle versus elsewhere on the wall. And then you calculate this ratio. Now, this ratio is going to be, approximately equal to it's going to be the probability that you land. So this is the probability you land inside the circle is just basically going to be the area of circle divided by total area, which is equal to, well, if we think about it, the area of the circle, well, the radius is 1, so that's 2 pi. And the total area, well, it's 2 wide by 2 tall, so the total area is 4, right? I did that right? So then this should equal to pi over 2. Let me make sure I did that right, because in my head it should be pi over 4. Yeah, it should be, yes. Yes. You guys, you can correct me. Of course it's not 2 pi. So the area is pi r squared. So this should just be equal to pi. So this is pi r squared. And then this down here is just basically r squared, not r squared, 2r squared. So that gives me 4, and that gives me pi, because r is equal to 1. So what this shows me is that if I throw lots and lots and lots of darts here and estimate this fraction, then that fraction will converge to pi over 4. So then if I multiply that fraction by 4, I have an estimate of pi. If I want a better and better estimate, a more precise estimate over time, I just throw more and more darts. So this is a way to, so more draws means better convergence on pi over 4, which is effectively on pi. So because you just multiply by 4. So there's a bunch of different ways to estimate pi by drawing random numbers, by dropping toothpicks on picnic tables. There's all these methods here, but they show you the power of randomness, because randomness involves probability expressions, which sometimes involve ugly constants that we might not easily have access to. But because we just know that the probabilities are given by the areas and the areas have a pi in them, then we can get pi by doing this experiment. That's a Monte Carlo method. So you just run lots and lots and lots and lots of experiments, and you take an ensemble, and that ensemble you then do something with, like take an average of, and then it allows you to back out some important quantity. Okay, so Metropolis wanted to sort of use this to deal with this equations of state problem. So any questions about this? Okay, so Metropolis, Metropolis, and equations of state. So again, he wants to like find things like the ideal gas law, which is PV equals nRT, where things like P and V, these things are macroscopic variables. So these are observables. So these are things you actually could measure with tools, like in a laboratory. But then the question is like, how do I explore these computationally? Because if you can find in a system, if you can find all the pressures and all the volumes, and you can correlate them together, then you might be able to derive an equation of state. You say, aha, it's always the case that pressure and volume are inversely proportional to each other, and their constant proportionality seems to be related to temperature. And that's effectively what we're seeing here. So how do you get that? Well, if you have a distribution of um, microstates, then theoretically speaking, you can solve for the expected macroscopic variables. Let's say, because a lot of times these are just averages. So I would like to integrate. So I'd like to basically say that I want to take the average E over my probability distribution, over my macrostate, of some function, which I'll call capital F. So this here is a function of my macroscopic. This is my instantaneous macroscopic variable. So the idea here is if it is possible to say this microstate, what pressure corresponds to this microstate, then you have a function which maps microstates to the pressure exerted by that microstate. And then the pressure we all feel will then be the average pressure over the ensemble of all of those microstates. And so I would like to take the average over the probability distribution. So this is our macrostate uh, probability density function. And then so that is going to be equal to the integral over all microstates of the function evaluated at the microstate times its probability distribution or its probability density function evaluated at that state. And I'll say D state. So where this thing, this is our distribution, which is our Boltzmann. And so by, this integral here is taking a so-called ensemble average over all of the microstates. So this is the computational problem to solve, is that you have a description of a physical system, you have you say all of its microstates are according to the Boltzmann. Given that all of the microstates are distributed according to the Boltzmann, if I integrate out over the kind of nuisance variable of energies or microstates or whatever, I can end up taking an ensemble average of my equation or of my macroscopic variable. And then that will end up giving me something, this is, as an example, this is like pressure or volume. So I'll say pressure is an example. And then that will tell me that for this macrostate in this particular configuration, we would expect this pressure. And so if you did these over and over again for lots of different macroscopic variables, you could explore equations of state. So then the question ends up being, how do you solve this integral? This ugly integral that has lots and lots of degrees of freedom and has this ugly distribution right here. Now, what Metropolis realized or started to realize there, as others were, is that you could use Monte Carlo integration as a start. So rather than doing the integration that you might have learned in calculus class as a junior in high school or something like that, where you divide everything up and you kind of sum things together and take areas underneath the curve. So like if I were to draw, a function here, if I think about like Riemann integration or something like that, it turns out that if you want to integrate under a curve, you could take all of these individual areas. So you could approximate integral as the sum of all rectangles under the curve. That's one way to do it. But now that people had been thinking about randomness and whatever, then they realize, well, actually, do I really need to do all of those rectangles? In reality, alternative is I can say, well, you know what? I know that if I have a random, for a random variable X, I know that if I have, a bunch of realizations of that random variable, so I'll go up to X sub M, if I just take their average, that thing, as M goes to infinity, is going to converge to the expected value. Where this here is taken as the expected value over this probability distribution of X. So this suggests that if I know if I know a probability distribution, in order to calculate an expected value, I could do this ugly integral. Or if I have a way to just sample from that probability distribution, then if I add up a number of enough of those samples and then divide by the total, then that's going to be a good approximation of that thing. Well, it turns out that you can generalize that to functions. So I could say, alternatively, I could say, well, if I want to take the integral, if I do a function g and a random variable x, then I can say I'm going to type that on those realizations of that random variable, and I'm going to take the average of them, and that thing is going to converge to the integral over x of g of x times that probability distribution dx. And so I can take random samples and average to approximate integral here. And that, this is the beginnings of so-called Monte Carlo integration, is that by using a random sample, I might need to do less work in order to approximate this integral. And we'll pick up this and close this off next time, but the problem here is what happens if you're trying to take this integral, and that P of X is the Boltzmann, and the Boltzmann is near zero for most of your samples. then that means that you're going to have to do a whole lot of samples, because most of your samples will not be taking a bite at the apple. Most of your samples will not be sampling the area of the Boltzmann that has most of the probability. So it would really be nice if we had a way, and as we'll see, to sample directly from a Boltzmann distribution. And if we can sample directly from the Boltzmann, then we can do this approximation with far fewer samples. And then that's why Metropolis came up with the Metropolis algorithm to sample from the Boltzmann. And then that approximation, that algorithm that allows us to sample from the Boltzmann, we can then use in other MCMCs and in simulated annealing. So that's what we'll talk about next time, is the Metropolis algorithm and how we actually sample directly from the Boltzmann rather than try to sample oversample with a uniform distribution and then just account for it, which is what you'd have to do otherwise. All right, that's all I got for you today, and we'll finish up then Thursday.